So, let's try that. So, let's go back to our maximum likelihood function that I had written earlier. Let me recall that. This was, I noted down this as star earlier. So, the likelihood function look like this, the log likelihood function look like this, sum over I equals 1 to n logarithm of, well, sum over k equals 1 to k pi k e power minus xi minus mu k squared by 2 sigma k squared into 1 by square root 2 pi sigma k. This was our complicated looking log likelihood function, and the problem that we had was that there is a summation sitting inside the logarithm. Now, what we can do is, well, I'm going to think of this as sum of a bunch of things. Now, Jensen is telling us that, well, it's not just a sum of a bunch of things, it's sum of a combination of a bunch of things that can be written in a form where you can remove the sum outside, pull the sum outside, and then you will get an inequality. So, we need some combination of the sums, right. So, it is just a bunch of numbers sitting here. I am going to think of these as a bunch of numbers, and then there is a sum here. Now, I do not have these combinations yet. So, what I am going to do is, I am going to introduce these combinations artificially and make it a problem with more parameters. I mean, it looks counterintuitive at first glance, but then we will see the power of this method. Now, what we are going to do is we are going to introduce for every data point I, what we are going to do is we are going to introduce some parameters, and let us call them lambda I1 to lambda Ik. So, every data point gets k new parameters, right. And what are these? Well, such that what should happen is, for every data point I, the lambdas that we are introducing should be, should have this notion of probability, right. So, they have to sum to 1. So, lambda Ik should be 1, where 0 less than or equal to lambda Ik less than or equal to 1 for all k, or all I and k actually, right. So, what is this? What does it mean to say introduce suddenly new parameters? Let's see what that means, right. So, we have log L of theta, and this is sum over I equals 1 to n log of sum over k equals 1 to k, and this is where we want to introduce, and then let me just bluntly put this lambda Ik, which is the parameter that I am introducing. There is one for every data point I, and for every data point I there are k of them, capital K of them, and the small kth parameter is lambda Ik. Okay. Now, I am just multiplying it, which means that the sum that I am thinking of cannot change, right. So, then I am looking at a different function. So, to do that, what I am going to do is, let me write down what the sum was earlier. So, the sum earlier was pi k e power minus xi minus mu k squared by 2 sigma k squared 1 by square root 2 pi sigma k, which is exactly the density of the Gaussian, but because I have multiplied it by lambda Ik, I will divide it by lambda Ik. Now, it is just multiplication and division. So, it is still exactly the same log likelihood, but then I am just artificially introducing these parameters. I am multiplying it, dividing by parameter. Remember, for every I and every k there is a lambda Ik. What does that mean? That means that for every data point, now I am saying there is a distribution over all k's, all clusters. We will try to interpret these lambda Ik's later on. For now, think of them as some artificial parameters that I am introducing into the picture. The moment I do this, now I observe that, well, this is a log of a sum of weighted combination of a bunch of points, right. So, the logarithm is evaluated at the sum of lambda Ik times a bunch of things. So, which means I can use my power of Jensen's, right. So, now by Jensen's I can write this log of L of theta, which is exactly this quantity, as greater than a different function. It is not the same function, right. So, because the function changes, and then that is why you have an inequality. And let me just call that as a modified log likelihood function, log likelihood of theta. Now, this theta were the earlier parameters. Now, you have this extra parameters lambda which have been introduced. Now, I am creating a new function which is a modified log likelihood function, which not only has theta and then lambdas, but then what is this modified likelihood function? Well, it is basically the log likelihood function with Jensen's applied to it. The moment I apply Jensen's, the summation comes out, right. So, this becomes sum over k equals 1 to k lambda I k. Let me retain the color for lambda I k, so that we see that those are parameters we have introduced into the method. Now, you have logarithm of pi k e power minus xi minus mu k squared by 2 sigma k squared 1 by square root 2 pi sigma k divided by our usual lambda I k, right. The equations might look complicated, but then what is exactly happening is we had a log likelihood function which was hard to maximize, but then we observed that there is a log of sum sitting inside it. Now, we are introducing these extra lambda parameters and then writing it as a sum of logs, and that is just by Jensen's, by noting that log is a concave function. That is all has happened so far, right. Now, why is this any easier, right? So, why should this be any easier to solve? First of all, I mean, is it easier to solve this maximizing this modified log likelihood function? Because first of all, it is not the thing that you wanted to solve, right. So, it is not the log likelihood function, it is a different function. The second thing is that it has more parameters. We have introduced all these lambda I k's for each I and each k, which means we have introduced n into k parameters essentially extra into the system, into the equation, right. So, it should be worth it, right. So, that something should be super simple, something should become really simple, otherwise, doing all this is not worth it. Now, we will see why this is worth the effort. Now, first thing we note that the above modified log likelihood gives a lower bound for the true log likelihood. At theta, I wanted to maximize the true log likelihood at theta. The function that I care about is true log likelihood at theta. Now, if you give me a set of parameters theta, then I can evaluate the true log likelihood at theta. But now, if I evaluated the modified log likelihood, now it is going to give me a lower bound. That is what Jensen tells me, and this lower bound, and the interesting part is that this is a lower bound for any choice of lambda, right. So, Jensen's holds no matter what your lambda is, as long as lambdas sum to 1, lambdas are between 0 and 1, right. So, for any choice of lambda, when I say lambda, when I say, again, just to be clear, when I say theta, it means that I mean mu 1 to mu k, sigma 1 squared to sigma k squared, pi 1 to pi k. When I say lambda, I mean lambda 1 to lambda 1 k, lambda 2 1 to lambda 2 k dot lambda n 1 to lambda n k. That is what I mean by saying we are introducing this extra parameter lambda. So, no matter, so you give me a theta, which is a bunch of mu, sigmas and pi's. Now, I mean I don't want to evaluate the log likelihood. Instead, let me say I want to evaluate the modified log likelihood. Now, I can put any value of lambda, I will get a number and then give it to you, and that number will be a lower bound for the actual log likelihood at the theta that you gave me, right. So, I will use your theta, I will use my own lambdas, and then I will compute the modified log likelihood, it will be a lower bound. That is simply by Jensen's. But the question is, but what are we gaining, right? So, okay, so this is a lower bound, all right, so all that is good, but what are we really gaining by introducing this? We need to understand that, right? And here is the key insight why this is such a beautiful method, right. So, the key insight is the following, and that is why it works so well, we will see later. Now, I originally wanted to maximize my likelihood function with respect to theta. Now, I have a new method, new function which is a modified log likelihood, which is a function of two different parameters. One is theta and one is the artificially introduced parameter lambda. Now, the great advantage we gain by looking at this modified likelihood is the following, and we will justify this in a minute. Now, the advantage is that if we fix some lambda, it is easy to maximize with respect to theta. So, for a given value of lambda, it is super easy to maximize with respect to theta. Similarly, we will see if we fix theta, it is easy to maximize with respect to lambda. This is perhaps the most important thing we should take away from here, right. So, now originally we had a problem which had only one set of parameters theta, and we do not know how to maximize that in a nice efficient way. Now, we are saying we are introducing another set of parameters, and now we are saying that if I fix some value for that parameter, I can maximize this modified likelihood with respect to theta very easily, and if we fix theta, then we can maximize it with respect to lambda very easily. So, how is this useful to come up with an algorithm, we will see in a bit, but then let us first convince ourselves that this key insight is true, and what does it mean to say it is easy to maximize with respect to theta and lambda by fixing the other thing, and then we will actually put down an algorithm, right. So, now what does it mean to say we will fix lambda and maximize over theta? Let us first do that, right. So, fix lambda and maximize over theta. Okay. So, what is the actual function? Well, this is maximize over theta. When I say theta, again the set of parameters that we have been looking at, sum over I equals 1 to n, sum over k equals 1 to k, lambda I k, logarithm of pi k e power minus xi minus mu k squared by 2 sigma k squared into 1 by square root 2 pi sigma k by lambda I k. Lambda I k. Now, we are going to, when I say we fix lambda, we are going to treat lambdas as constants, right. So, what does that help? How does that help us? Well, this guy is same as maximizing over theta, sum over I equals 1 to n, sum over k equals 1 to k, lambda I k log. Now I can think of this as, there is a product sitting inside the log, right. So, that will become a sum over logs, right. So, this will become log over pi k. Now, the second term things will cancel out with respect to the e, right. So, this will become minus lambda I k xi minus mu k squared by 2 sigma k squared minus lambda I k log square root of 2 pi sigma k. The next term I can ignore because this is lambda I k log, minus lambda I k log lambda I k, but then this I'm kind of treating it as a constant, lambda is constant because that is what saying fixed lambda means. So, this is equivalent to maximizing only with respect to these three terms, because the real parameters here are pi k, mu, sigmas and so on. So, only these three terms matter. Now, the advantage of looking at this is that if you now take the derivative of this function where you are treating lambda as constant with respect to the parameters theta, that is with respect to mu, sigma squareds and pi's, all of them have a closed form, and let me put down those closed forms, right. So, now if you can take derivatives, I will not do the derivation here, and please try that, and that is a very insightful exercise to try that. Take derivatives with respect to mu's and sigma to get the following, right. Mu hat, I am going to call this a modified maximum likelihood. It is not the maximum modified likelihood, right. So, we are not maximizing the original likelihood, we are maximizing a modified function. The kth value is going to look like sum over I equals 1 to n lambda I k xi divided by sum over I equals 1 to n lambda I k. We have a closed form for mu's, right. So, if we fix lambda and try to maximize the modified likelihood function with respect to theta. Similarly, sigma squared hat mml for k will just be sum over I equals 1 to n lambda I k xi minus mu hat mml k squared by sum over I equals 1 to n lambda I k. We will talk about the pi's in a bit, but let's look at this and understand what this means. This means that there is some lambdas which I am fixing, right. So, I can arbitrarily fix this lambdas, and then if, for instance, if I had fixed lambda I k, the way to think of lambda I k is as follows, right. So, you can treat lambda I k as the probability that the ith point goes into the kth cluster. What you think is the probability, because we are fixing it arbitrarily at this point, right. So, let us say I put each point into one cluster, right. So, I want to assume that every point comes from a single cluster. So, which means lambda I k will be 1 for a particular cluster indicator value k, and then it will be 0 everywhere else. If that happens, then what is this essentially telling us is mu hat mml k is simply the mean of the data points assigned to a particular cluster, and sigma squared k mml is just the sample variance of data point assigned to a particular cluster. If our lambda I k's are 0 for all k's except 1, for which it is value is 1, but then we are not constrained to put lambda I k's like that. Now, then you can think of lambda I k's as somehow, starting with a soft clustering of the data points, which means, what do you mean by soft clustering? For every point, I am kind of telling what is the chance that this point comes from each of the clusters. Now, we do not know earlier how to get this chance, but then let us say we initialize it with some values. Then what is this? These estimators are telling us is that, well, it is going to give you a weighted mean and weighted sample variance, where the weights are given by these chances that we are fixing. That is all this is, right. So, basically once I fix lambdas, then maximizing the modified likelihood is very easy, right. So, it is like saying I am telling how important is every data point for each cluster. So, I am just going to simply weigh these points by their importance for each cluster, and that will give me the cluster's best mean and the cluster's best variance. That's exactly in equations these things that you are seeing. Now, you have to be slightly careful when you are maximizing with respect to pi's, because pi's have this constraint that they have to sum to 1. Nevertheless, we can do the maximization. You can do maximization of pi 1 to pi k, pi capital K. Now, if you again go back to your likelihood and see which are the terms which depend on pi, it will simply be there will be just only one term, and that is also not a too complicated term, lambda I k logarithm of pi k, such that pi's are not free variables, such that sum over k pi k equals 1, such that pi k is greater than or equal to 0. Now, you see that, you observe that, well, there is a lambda I k for each I. For every I, we are deciding on a distribution over the data points, right. So, sorry, distribution over the clusters. Lambda I k tells me what is the chance that the ith point comes from the kth cluster. Intuitively, that is what it is meant to mean. So, now here this is a sum over I equals 1 to n and something which sums up over k. Now, we are trying to maximize with respect to pi k's. Now, what we can do is we can solve, of course, there is a constraint here, which is what will typically cause an issue, but you can solve this using standard constraint optimization techniques. If you've seen some constraint optimization techniques, you may be familiar with the method of Lagrange multipliers. Otherwise, take it at this point that this can be solved in closed form easily, right. So, this can be solved using the method of Lagrange multipliers to give us the following quantity: pi k mml is going to be simply sum over I equals 1 to n lambda I k divided by n. Now, what does this intuitively mean? Well, this intuitively means that, well, remember lambda I k kind of tells us what is the chance that we think ith point goes to the kth cluster. And now we are asking what is the chance that some point will come from the kth cluster. Well, it is you basically have to average the chance of each point going to the kth cluster. Now, if each point was hard clustered, that it will only go to one cluster, which means lambda I k's were taking values either 1 or 0, then this simply means that pi hat, our best estimate, is just the average of the number of points or the fraction of points that went into that particular cluster, right. So, if lambda I k's were zeros or ones, then, well, for each data point you are counting lambda I k, right. So, then it will be 1 only for those points which have been assigned to cluster k. So, you are just looking at the fraction of points assigned to cluster k. But then if you do a soft clustering, if lambda I k's are between zeros and ones, then this is kind of telling you on an average what is the chance that a point belongs to a cluster k. That is what this is, right. So, basically putting everything together, so what we have is that we have the following, right. So, fixing lambda, we get the following. If we maximize with respect to theta, we get the following. I will just summarize this as mu hat mml k is just the weighted mean, where the weights are given by these lambdas that we are assuming, lambda I k, sigma squared mml k is the weighted sample, is the weighted covariance, sample variance, where again the weights are given by lambda i's that lambda I k's that we are assuming, sum over I equals 1 to n lambda I k, and pi's are again the weighted version of what you would standard expect in a, if it is just the weighting of each point's chance that it belongs to cluster k and then averaged. So, this is good. So, this kind of tells us that, well, I have a problem with two sets of parameters theta and lambda. I fix lambda, I can maximize easily with respect to theta. Now, the other way should also happen easily, right. So, you need to fix theta and maximize with respect to lambda, and let us see if that is easy also. And once both of these we convince ourselves that these are easy by looking at the actual closed form solutions, then we can put down an algorithm that can be efficiently used to solve this problem. Okay. So, how would this look like? So, now we are fixing theta and then maximizing with respect to lambda, which means again let me recall the likelihood function. Every time I would have to write this, but it is worth doing that because it will reinforce what we are trying to do in a better way. Okay, divided by lambda I k. This was the likelihood function. Now, I want to maximize this with respect to lambda, treating all the other parameters mu's, pi's, sigmas as constant, right. Now, I can do some simplification and then only pull out the terms which are non-constants, and that will look like this lambda I k, and you can try this one step I am skipping, but then you can try this out for yourself, right. So, so lambda I k some constant, and I will write what this constant is, minus lambda I k log of lambda I k, where this constant that I am thinking of is pi k e power minus basically the density of Gaussian, right. So, 2 sigma k squared 1 by square root 2 pi sigma k. Okay. So, now remember we want to maximize this with respect to lambdas, right. So, and then there are k lambdas for each data point I. Now, if you look at this equation itself, it is a sum over data points, and then for each data point I have a bunch of k parameters, right. So, and then I am adding these things up. So, because the the function is does not have any cross terms, right. So, the lambda I k and lambda j k do not appear together at all in the function, right. So, I can actually maximize these separately for each data point I, and then that would actually, the separate maximizers would actually also maximize the entire function, because it is just a sum of a bunch of functions which depend on I separately, but then there are no variables shared between these, the inner summation. So, I can optimize this separately, which means that we can fix any I and then maximize over lambda I1 to lambda Ik, sum over k equals 1 to k lambda Ik log of Aik minus lambda Ik log of lambda Ik. Of course, lambdas can't be arbitrary, such that we know that lambdas have to satisfy k equals 1 to k, lambda Ik is 1 and 0 less than lambda Ik less than or equal to 1. It is a constraint optimization problem, nevertheless not a hard one to solve, right. So, you can still maximize this in closed form using the method of Lagrange multiplier, can be solved to in closed form analytically. When I say analytically, all I mean that you can write down a formula for the answer to get the following formula: lambda hat Ik of the modified maximum likelihood looks like the following, right. So, 1 by square root 2 pi sigma k e power minus xi minus mu k squared by 2 sigma k squared into pi k divided by sum over k equals 1 to k 1 by square root 2, well, maybe I should use a different number, L sigma L e power minus xi minus mu L squared by 2 sigma L squared into pi L. Okay, so this looks like a complicated formula, but it isn't, right. So, this is all this is saying is that, well, what is this, right. So, I am trying to ask, well, if I fix the parameters, if I told you what are the means, what are the variances, what are the pi's, then what is the best guess for lambda hat Ik? What is lambda hat Ik representing? It is representing the probability that the ith point goes to the kth cluster, right. So, I tell you what the ith point is and then ask what is the chance that this goes to the kth cluster. Now, well, if I know all the parameters, then basically what I am asking is, I am asking something like what is the probability that Zi, which is, remember from our step 1 that this is the cluster indicator, is k given xi, right. So, given a point xi, I am asking what is the chance that this goes to the kth cluster, and that is what I am going to think of as lambda hat Ik as to represent. Well, I know by Bayes' theorem this is just probability of xi given Zi equals k into probability of Zi equals k divided by probability of seeing xi. This is my Bayes' theorem, right. So, this is what my Bayes' theorem would tell me. And now, if I have the parameters mu's, sigma squareds and pi's, then you can verify that this is simply probability of xi given Zi equals k, because this is the chance that xi comes from the kth cluster. This is simply probability of Zi equals k. This is the step 1 chance that the kth cluster is chosen, and this is summation over L all possible ways of generating xi, probability of xi given Zi into probability of Zi, which is just probability of xi itself. This is just Bayes' theorem, right. So, it is so nice that this turns out to be exactly what you get if you had applied Bayes' theorem and tried to estimate probability of Zi equals k given xi. That is, what is the chance that the xi point goes to the kth cluster, and that once the parameters are given, you will simply use the Bayes' theorem to estimate that. That is exactly what comes out as the as your maximum likelihood estimator also. Okay, so now what we now have is we have solved for lambdas if the parameters are given. Similarly, we have solved for the parameters if the lambda are given, and all of these are just simple formulas, right. So, given once you fix lambdas, you get a weighted mean, weighted variance, and then a weighted fraction for mu, sigma squared and pi respectively. And if you fix mu, pi, sigma squared respectively and then see what is the best lambda, then that is simply by your Bayes theorem, then estimate for probability of Zi given Xi, right. So, all of these are simple now, right. So, all of these are closed form solution. So, which means we can actually write down an algorithm for this, for solving for theta, right. So, remember our original goal was to maximize the log likelihood. Now, by adding this extra parameter as lambda, we are saying that you can fix lambda, solve for theta, you can fix theta, solve for lambda efficiently, that we have seen how. Now, we will use this to come up with an iterative algorithm to solve the problem.